And quick introduction for myself. I am Joe Cusimano with Escrypt Sales in North America. I run the North American cybersecurity sales team for Escrypt. Been with the company about 3.5 years and been in automotive, embedded automotive electronics for my entire career, closing in on 30 years now. John, if you could unmute and give a quick introduction, that'd be great as well.
Joe, thanks Freddie for having us. My name is John McShane. I'm the lead security tester for Escrypt North America. I have been at Escrypt about the exact same time as Joe. We actually onboarded together, so I'm about 3.5 years. And I don't have as quite as much as 30 years as Joe has, but I have about 9 years in automotive and cybersecurity within the industry.
Thanks, John. So I'll be covering section 1 here. Why is fuzz testing important in the growing vulnerabilities of the connected world? And then John will take over the meat of the presentation here with sections 2 and 3. So here we go. So why is fuzz testing important and the growing vulnerabilities of the connected world? The connected car has been around a long time. If you're like me, you know, especially in the North American fleets, OnStar and different connectivity have been in cars for a long time. But what's unique about the last few years and what's coming in the future is not just the ubiquity of the entire fleet being connected. It's the higher bandwidth connectivity and the added features that make these vehicles more complex today. So 5G, especially as 5G rolls out in the world, the bandwidth to the car increases. The amount of connected features in the car that are already in the vehicle are increasing, and then the amount of additional connected features that will get added to the vehicles in the coming decade continue to grow as that bandwidth grows. So it's not a static event. It continues to evolve, and that threat surface in the vehicle continues to grow. So hence protecting these vehicles and protecting these networks in the vehicles and the devices in them becomes, you know, an indispensable thing that we have to do as the vehicle becomes a rolling endpoint in the connected universe of all our devices. So hence cybersecurity testing of the vehicle becomes paramount. It becomes very important as to develop a very methodical approach to doing cybersecurity testing as part of the development process to prevent manipulation and attacks and these types of things. So when it comes to fuzzing and how fuzzing becomes an important part of that methodical approach to doing cybersecurity robust testing is important, as again here our little image on this slide shows all the different types of threat surfaces that can exist in a car, the different types of connectivities that exist in a car, the networks that exist in a car. So where fuzzing comes in is that this is essentially the first step of a black hat hacker kind of attack, is determining where there might be a vulnerability and attempting to gain unauthorized access and establish that entry point. So the second step of a kind of a black hat attacker to go ahead and determine that entry point is what we call a fuzz attack. And this fuzz attack could include any multitude of techniques that will flood the system, the vehicle system, or an individual component with unknown, unexpected, or random inputs. And this is done in an attempt to find a weakness or an entry point for unauthorized access. So step 3, fuzz testing, is then, or what we call fuzzing, is then the methodical and automated test procedures that we use as cybersecurity engineers to mimic that potential fuzz attack that a black hat hacker would do. So this is essentially the high level overview of what is fuzzing and why it's important. It is that very automated and methodical approach to flooding a vehicle system with unknown, unexpected, and random inputs. And as you can kind of imagine, in a vehicle today, there's hundreds of ECUs, and some of these ECUs have the most simplistic functions. And even those can become something that is a simple warranty issue. A hacker could find a vulnerability on something very simple and create warranty issues. But in a more catastrophic example, a safety critical ECU, any of these ECUs that exist today, stability control modules, powertrain and engine modules, instrument clusters, braking modules, and now with the onset of self-driving vehicles or just driver assist systems, any of those driver assist systems become safety critical ECUs. And knowing how these ECUs respond when invalid data is flooded onto the CAN or communication bus or Ethernet bus becomes a vital thing to test for and know and make sure that you've designed out of your process any of these potential problems that could go wrong. Things like the ECU just stops responding, it could reset, it could respond with excessive error frames onto the CAN bus and then insert additional traffic onto the CAN bus, which causes even more problems. So none of these are the types of behavior you really want your ECU to do during a vehicle operation. And these are the things we try to protect against with fuzz testing or determine and design out of the system with fuzz testing. And here's a quick snapshot of an entire CAN bus frame. And you can imagine if any one of these bits is out of place or unexpected and then repeated over and over again, these are the types of things that can cause problems on the CAN bus or in the communication bus. And this is what we use fuzz testing for to test for and design out of the system, hopefully design those vulnerabilities out of the system. So that's a quick overview of why fuzz testing is important. I'll hand off now to John to go through the basics of fuzz testing. And John, I'll make you the presenter now and hand it off to John.
Thanks, Joe. So fuzz testing, a lot of people ask, what is fuzzing? They hear it all the time in the industry, but I think this diagram really explains it very well, what fuzz testing is. Typically for fuzz testing, you will have a computer, which is going to be like your client, and then you're going to have a fuzz engine, which is generating the fuzzing. That's where all the magic happens, and then you have a target. So then based on what's sent to the target, you then do what's called instrumentation, and you pass or fail, and you repeat this kind of flow millions of times potentially, or thousands of times. That's why fuzzing is really successful, because you're just running so many test cases. Basically, the fuzz engine is generating random data. It could be hard-coded data that are common test cases that fail, or it could be common failure bytes. There's a lot of research on like 7F, 7E00, FFs, certain data bytes that will actually cause the code to not do something that it's handling. A lot of times that is because of the fuzzer might send like a signed or unsigned characteristic, when if we send a sign and the code's looking for unsigned, the code might have an unhandled exception. But basically we continue this process over and over again with the fuzzer and monitoring if it passed or failed. And then this helps find vulnerabilities within the code and undefined behavior. So fuzz testing is not penetration testing per se, but it's a technique that's often used by, like hackers actually. What we do at Script, we're more of a white hat hacker, where we get paid, from a customer actually to hack their product and publish a report directly to them on any vulnerabilities we have. So just to kind of get it, straight, fuzz testing isn't penetration testing or hacking, but it is a technique used that a lot of times is will be an exploratory technique that can then lead to an exploit that a hacker will use. So to make a fuzzer successful, there's several things that it needs to actually be successful. I kind of listed in 3 different areas. That would be crash detection, anomaly detection, and then smart fuzzing. Just because you run a fuzzer doesn't mean it's actually effective. And there's a lot of different ways to make a fuzzer smart, so to speak, that I'm going to talk about. But the first thing you need to do is detect crashes. How are you going to do that? You can look for invalid responses from the target when you send an invalid input to it. You can look for an insecure response. Is it leaking more data than I expected it to send? Changes in periodic messages. If you have some sort of IoT or automotive controller that sends messages every 50 milliseconds, and I then see it at 120 milliseconds, that's not, good behavior. And you can also monitor amperage. So when you're working on these IoT or automotive controllers, if it's currently usually pulling 0.5 amps and I see 0.1 amps, it's highly possible that the actual watchdog timer within the controller reset, which would change the amperage. So once you have the crash detection of how you're going to look for failures, you can also look for like anomaly detection, and that would be like undocumented behavior, this like a certain service trigger that's not supposed to be in the database file. It could be excessive processing time. Basically, you're just looking for behavior that's not within the actual requirements of the device. And then to get to the actual smart fuzzing, there's several different ways to do that. And an easy way is just to input a file into the fuzzer that the device looks for. So if we're talking an automotive controller, typically that's going to be using a CDD, an ODX, a PDX, a DBC, an AirXML, any sort of AUTOSAR input. I then know what's going to be in there, and I can trigger certain test cases. Another way is to make the fuzz engine smarter. It might use certain combination of bytes that typically indicate failures. Another way to make a fuzzer smarter is to actually add artificial intelligence. The artificial intelligence can really help, steer the fuzzer in the right direction just by being able to look at how things failed and didn't fail. So touching more on how you can make a fuzzer, smarter, this kind of demonstrates how adding artificial intelligence to a fuzzer can really help the fuzzer. But basically, you have past test cases and failed test cases, and that then goes to a neural network where we'll pre-process the data. So basically, you could take a log, look at the log, generalize all the data, so maybe like 10,000 test cases, and then you can kind of label it from a 0, 1, like a 1 would be a passing, a 0 wouldn't be passing. But based on all those learned test cases, then the fuzzer can generate new test cases. The advantage of adding the artificial intelligence is it makes the fuzzer extremely smarter, but the big thing is it covers more code paths. Fuzzers are unsuccessful a lot of times because they don't cover all the code paths. If you don't cover all the code paths, then you potentially leave vulnerabilities in a controller. So with the automotive controllers, you can have, thousands on thousands of code paths, even millions potentially. So by adding, smartness to it, you can ensure that you cover a lot more code paths than you would if you didn't add artificial intelligence to the fuzzer. When it comes to fuzz testing, there's other things you can do to actually aid your fuzz testing. That would be, like I touched on earlier, amperage monitoring, using an external power supply to help manage the actual amperage. You can also add power cycling. This is extremely important when you're fuzz testing. So a lot of times when we're doing fuzz testings, the controller or device might have an unhandled exception where it's not recoverable, and then the fuzzer is going to be stuck at 5% of its test cases, for example, and that's never very fun, coming into a Monday on a work day and finding out your fuzzer only did 5% of what you wanted it to do. So in order to help prevent that, you can actually tie in a power supply that when it sees a failure and the device doesn't recover, it will then reset the controller and then the fuzzing goes back on. Ideally, you have that all automated, so then you don't need to do anything. Another thing that can help aid a fuzzer is camera detection. So at SCRIP, we do work on infotainment systems, and they have screens. When you're working on an engine controller, you don't have a screen. It's an engine controller. But say for an infotainment, you have a screen. A lot of times when you're working on infotainment, on the actual CAN bus or message side on Bluetooth, everything might look fine, but the screen doesn't look very fine. It might be a blue screen, a black screen, weird text could be populating that shouldn't be there. But to help aid the fuzzer and give it more data, when you're instrumenting to figure out if something passed or failed, you can actually use a camera to look for what a known good image is and then a not so good image. And basically when it sees unexpected behavior on the screen, the camera then takes a picture for the test engineer to take a look at, and it'll show what test case it occurred around roughly. The other thing that helps a lot with fuzz testing is combining your Wireshark logs, your amperage monitor, and power cycle. Basically, you can combine all this data into your fuzz report, and you can help debug with a software developer what actually happened. So all these things that I'm mentioning, amperage, monitoring, camera detection, power cycling, all help aid the fuzzer, which is called typically in the industry as instrumentation. So what do we fuzz? We pretty much fuzz everything you can think of at script. We do CAN, classic CAN, CAN-FD, ISO-TP, UDS, and then if we're working on off-road, it'd be J1939. We also work on Ethernet, IPv4, TCP, Bluetooth, BLE, Wi-Fi, USB, TLS, TCP. Basically, all these protocols that you see running in IoT devices and controllers, it can be fuzzed. So at Script, we use off-the-shelf tools, that you can purchase. There's several commercial tools out there in the industry that you can purchase, or even open source code, such as like AFL, for example, that you can use for fuzz testing. But a lot of our fuzz testing, we use our own tool called CycrFuzz. The nice thing about CycrFuzz is it's designed around automotive products. So a lot of the fuzzers that you can get off the shelf aren't designed for automotive, and then they struggle with fuzz testing because they're meant for enterprise, not for actual automotive IoT. The other big thing about why, when I use CycrFuzz, why it's really nice compared to enterprise is it can execute up to like 50 test cases per second. The faster your fuzzer is, the more effective it is because the more test cases you can run. And how that's kind of done is a lot of fuzzers will use what's called a static sleep. So they say, I'm going to wait, 50 milliseconds every single test case. Well, if the device responds at 1 millisecond, basically I'm wasting 49 milliseconds that I could execute. If the controller responds, I should reward it with another test case, basically. So by using a dynamic test case on, a lot of the normal or common MCUs that are out there right now, we can execute around 50 test cases. The other nice thing is that, with CycrFuzz, I can input database files such as like a PDX, a CDD, AirXML, like I already touched on. By using that, I already know what messages the controller is looking for, which really helps aid the fuzz testing. And of course, having an actual GUI helps a lot. A lot of people or pen testers will run like a headless command line fuzz tester, which isn't the most fun to work with. And then if you give it to someone that doesn't have as much experience, running command line tools, it makes it very difficult. So having a front end really helps. The other nice thing that you want, and for fuzz testing, and what CycrFuzz does is it automatically generates reports. So basically, you want to click the button, you run the test cases, and you get a report. By not having an automated report, then a test engineer has to go through all the logs and see where the crashes occurred, and then generate a log manual, which can take several days potentially. And then as you can see in this picture, we have the past test cases. We have a fails count, which in this ECU, there was about 12 failures. You have runtime and estimated runtime. And you can also monitor the average test cases per second, bus load. There's several different things, that we're monitoring during this fuzz test picture. So let's get into some examples for fuzz testing in like the real world. So once you do a fuzz test and you get the results and you have all the data, you then have to typically make a comprehensive report that will a lot of times go to management or executive level potentially. We put in a report, and what's common to put in a report in the industry is a management summary of what the project was. For example, the fuzz test could be an engine control module for an OEM that we received, and the customer was looking for software robustness within that controller. The carried out test could be, what layers you're fuzzing at. So like UDS, ISO-TP, AirXML, there's a lot of different layers within the AUTOSAR stack that we can fuzz test and run different tests for that. And then even if the test was successful, the documentation or fuzz test report should still publish how that test was conducted. And then when there is failures, every failure needs to be assessed with a severity assessment and suggested countermeasures. This is very similar to like a CVSS score. This can be done with this actual CVS score, or you can, at script, we have our own scoring system that's a little bit more meant for embedded controllers versus CVSS. So in this slide, I'm going to talk about now. These are some real world projects that we've done at Script and show some of the basically the findings that we find within controllers. And this kind of shows, why fuzzing I believe is important. A lot of customers, they don't think fuzzing is important because they've never done it before. And in this slide, you can see some of the stuff we find. The big thing that we often find is we find a lot of stuff in the controller that shouldn't be in there. And that could be, for example, on this gateway ECU, we found a diagnostic that was not in the ODX, but it was in the code. We sent that command. Since the code wasn't finished, the controller stopped responding because it didn't have a fail path of how to handle when we actually sent that service. The OEM and tier one never caught it because they didn't know it was in the code, but then fuzz testing found it. And that's what makes fuzzing so successful is you don't know what you're going to find. And that's why it can be so good to have when you're running, an actual product. Another example on the top left side is we sent a sub-byte for an ECU reset that is in the ISO standard, but the OEM had a requirement not to use it. The controller actually still had it implemented because they had a stack where it was defaulted on. And basically when that was sent, the controller would stay in bootloader until we reset it. And the reason why that happened was because the developer and the customer didn't know that was in there, either did the OEM, and we found it with fuzz testing. The OEM thought it was so valuable that finding that they added that requirement to allow their testing. And that's a big thing with fuzz testing is it's hard to link some of these failures to requirements because if it was a requirement, it most likely would have been caught. So a lot of these failures that we find will be added to other requirements. So hopefully fuzz testing doesn't find some of these, it can be found earlier on. Another good example of, a failure on the bottom right corner, we had a telematics ECU where we fuzzed it via USB. And then on the USB side, the radio actually allowed keyboard strokes, which is really weird. And that's because of the OEM or tier one forgot to turn off certain classes that were in the USB. And basically we sent keystrokes over the USB and disabled the Bluetooth functionality within that radio. Does anyone have any questions or that, from a slide perspective, that pretty much is my presentation?